Think back to taking a highly complex math test in high school. You know, one of those multi-page algebra nightmares.
Oh, yeah. The ones where your scratchpad is just completely covered in furious scribbling.
Right, exactly. You cross things out, you erase formulas, you go down these total blind alleys. Maybe you even shed a tear or two in frustration.
Sounds like a typical Tuesday for me, honestly.
Yeah, same here. But somehow, at the very end of all that chaotic scribbling, you manage to write down the correct final answer in that little box at the bottom of the page.
And you just pray the teacher doesn't look too closely at the work.
Exactly. If your teacher only graded that final box, you got full points. I mean, it didn't matter one bit that your scratchpad was a complete mess of lucky guesses, flawed logic, and like 3 completely wrong equations.
You got the right answer, so you got the reward.
Right. And up until right now, that is the exact mechanism driving how we train our most advanced artificial intelligence models. We basically just check the final box.
Yeah. It's just kind of wild when you think about it.
It is. But today's deep dive is unpacking a brand new, state-of-the-art research paper that dismantles that paradigm entirely.
We're looking at a new framework called STRIDE. And really, the mission today is to understand how scientists are fundamentally changing the way AI models learn to reason.
So we're moving away from just checking that final answer box.
Yes. The researchers behind this paper have figured out a mechanism to evaluate the entire thought process, the actual, strategic reasoning on the scratchpad.
And they're doing it without needing a human teacher holding the AI's hand to grade every single step, right?
Exactly. Completely automated.
Okay, let's unpack this, because to really appreciate why this new STRIDE framework is so revolutionary, we have to start by looking under the hood of the system it's trying to replace.
And specifically, the fatal flaw baked into that system.
Right. So what is the current standard?
Well, right now, the industry standard for improving an AI's reasoning falls under an umbrella called reinforcement learning with verifiable rewards, or RLVR.
RLVR.
Yeah, and the most widely used method driving that is known as GRPO. The appeal of GRPO is its massive scalability. I mean, you don't need armies of human graders.
You just feed the model questions with objective, verifiable answers like math or code, and just let it run.
Exactly. But that scalability comes with a massive blind spot.
The final exam problem.
Yes. In standard GRPO, you give the AI a complex prompt. The AI generates a long, multi-paragraph response, which we call a chain of thought trajectory.
Okay, so that's the scratchpad.
Right. The system then looks at the very last thing the AI outputted. If that final answer matches the known verifiable answer, the system assigns a positive reward.
Seems logical so far.
It does, but the critical flaw is that the system takes that positive reward and applies it uniformly to every single word or token in that entire chain of thought.
Oh, wow. So it's like navigating a massive hedge maze.
Okay, yeah, I like that.
Imagine you're trying to find the exit. You take 3 completely wrong turns. You hit 2 dead ends. You spin around in a circle out of confusion, but then you just randomly stumble your way into the correct exit.
Right, you got out.
Yeah. But the current training system doesn't isolate the good navigation decisions.
Yeah.
It just looks at the fact that you escaped and says, great job, memorize that exact path.
Exactly. It rewards the dead ends and the wrong turns equally with the smart choices, entirely because you happen to get lucky at the end of the maze.
That seems incredibly inefficient.
It is. It's what researchers call sparse supervision. The reward is only distributed at the macro outcome level. Because of this, the AI gets 0 explicit feedback on its intermediate steps.
So just blindly reinforcing whatever it did.
Yeah. The model ends up reinforcing redundant, spurious, or totally lucky reasoning patterns. It solidifies bad cognitive habits because the overarching system just lacks the mechanism to say, hey, this specific logical leap was beneficial, but that tangent 3 sentences later was entirely useless.
I mean, scientists obviously flag this as a structural bottleneck pretty quickly, right?
Oh, for sure.
And the first major attempt to fix this issue seems incredibly logical if we just look at the surface. Like, if grading just the final answer teaches bad habits, the proposed solution was to look at the AI's scratchpad and reward it specifically during the moments when it's, quote-unquote, thinking hard.
Right, which sounds great in theory. In the architecture of large language models, thinking hard is actually quantifiable. It's measured by something called generation entropy.
Okay, generation entropy. Break that down for us.
So, to understand entropy, you have to remember how an AI generates text. It basically calculates the probability of the next possible word.
Word by word.
Exactly. If the model is reciting a widely known fact, the probability for the next word might be like 99%. That is low entropy. It's certain.
Makes sense.
But if the model is at a strategic fork in the road, the internal math might show that 5 different words all have a 20% probability, that mathematical flatness that's high entropy.
So high entropy means the model is uncertain. It's actively making a strategic decision.
Precisely. And when you look at an AI's chain of thought, these high entropy moments often correlate with words like, therefore, wait, what if, or let me recheck.
It's pausing to deliberate.
Yes. So, previous researchers built systems that isolated those high entropy moments and rewarded the AI for generating them, assuming that more deliberation simply equals better reasoning.
But wait, I have to push back on that. If the AI generates text that says, actually, let me recheck this, that could indicate 2 completely different realities.
How so?
Well, it could mean the AI just caught a mathematical error and is brilliantly correcting a mistake before it derails the final answer.
Right.
Or, and we've all been here, it could mean the AI is completely lost in the weeds and is spiraling in a circle of endless confusion.
Yes.
Just because an AI pauses to deliberate doesn't mean it's deliberating effectively. How does the system differentiate between brilliant self-correction and useless wheel spinning?
It doesn't. That is the exact scientific hurdle that derailed those previous attempts. Relying on entropy alone creates a massive false positive problem.
I see.
The researchers behind today's paper mapped this out extensively. What's fascinating here is that when you look at Figure 1 and Figure 2 in their source data, the token-level entropy graphs for completely correct answers and totally wrong answers are practically identical.
Wait, really? Identical. So the AI looks just as mathematically uncertain when it's about to be right as when it's about to be wrong.
Exactly. The peaks, the valleys, the overall frequency distributions of these high entropy tokens, they perfectly overlap whether the AI is brilliantly solving a physics problem or hallucinating a completely nonsensical answer.
Wow.
The density distributions are indistinguishable. So entropy alone is completely useless for determining if a specific reasoning step is actually beneficial to the final outcome.
And the paper actually breaks down the specific vocabulary associated with these high entropy moments, right, like in Figure 4.
Yeah, they do.
It says the chains of thought that lead to wrong answers heavily rely on high entropy phrases like guess, not sure, random seems, and unclear.
Right. While the correct trajectories heavily utilize words like derive, substitute, conclude, and verify.
But they're both high entropy.
That's the catch. All of those words, the beneficial ones and the detrimental ones, generate high mathematical entropy. They all represent moments of active, strategic decision-making.
So if your training system blindly rewards high entropy, you are reinforcing the AI's tendency to guess randomly just as much as you are reinforcing its ability to logically derive a formula.
You're just rewarding the act of pausing, regardless of what happens next.
And so we find ourselves in a real bind here. Grading just the final answer teaches bad habits because of sparse supervision. But rewarding the AI for high entropy also teaches bad habits because confusion and brilliance look mathematically identical.
It's a tough problem.
We need a way to verify which intermediate steps are actually the helpful ones, and we have to do it without a human reading the scratchpad.
Which perfectly tees up the core architecture of STRIDE.
Let's get into it. What does STRIDE actually stand for?
It stands for Strategic Trajectory Reasoning with Discriminative Estimation.
Quite a mouthful.
It is, but basically it bypasses the entropy trap entirely through a framework called Discriminative Strategic Reasoning, or DSR.
Okay, and how does DSR actually work in practice?
Well, it essentially operates like a massive automated game of spot the difference.
Spot the difference. I like that. Walk me through it.
It begins with a standard generation phase. For a single complex prompt, the policy model generates a group of different responses. Imagine it generates like 6 distinct attempts at solving the exact same problem.
Okay.
STRIDE then looks at the final answers of those 6 rollouts and splits them into 2 distinct piles. You have a successful pile where the verifiable answer was correct, and a failed pile where the final answer was wrong.
So once it has those 2 piles, what's next?
It gets highly granular. It scans through the entire text of all the responses looking at n-grams.
Okay, for anyone unfamiliar with the term, an enneagram is just a continuous sequence of words, right?
Exactly. And in this framework, the researchers specifically target phrases of 2 to 5 words.
Why 2 to 5? Why not just single words?
The length is highly intentional. A single word lacks the necessary context to represent a real thought, and a 10-word phrase is way too specific to be a repeatable strategic habit.
That makes sense.
2 to 5 words is really the sweet spot for capturing a discrete reasoning step. So Stride scans these n-grams and calculates a discriminability score for every single phrase.
So it functions kind of like a sports coach watching game tape in aggregate.
Oh, that's a good way to look at it.
Like the coach watches hundreds of hours of footage and notices a pattern. Every time the team utilizes a specific 3-step footwork technique, they score. But every time a player attempts a flashy spin move, they turn the ball over.
Right.
The coach doesn't even need to understand the physics of the spin move. The data clearly shows the footwork is causally linked to success, and the spin move is causally linked to failure.
The discriminability score executes that exact logic mathematically. It compares the frequency of a specific n-gram across the 2 piles.
So if a phrase is in the successful pile, mostly,
Then it receives a high positive score. It's identified as a beneficial strategic pattern. Conversely, if an n-gram correlates highly with the failed pile, it receives a negative score and is treated as a harmful pattern.
that is brilliant. It maintains the verifiable final outcome, but it traces that ultimate success backward to identify the specific micro-decisions that actually caused it.
Exactly.
But wait, applying this mechanically introduces a new problem, doesn't it?
Which is,
If the system is simply counting how often certain words appear in successful answers, it runs the risk of giving massive rewards to boring routine vocabulary.
yes.
Like routine execution phrases such as, and then we add, or just basic grammatical structures. Those probably appear in successful answers constantly, but they aren't the actual cognitive reason the answer was successful.
Anticipating that exact flaw is what makes the Stride framework so robust. Because you're right, if a system relies exclusively on the discriminability score, it ends up over-reinforcing routine execution-level continuations.
The AI would just get rewarded for generating basic grammar rather than executing deep reasoning.
Right, so Stride solves this by introducing a secondary filter. It combines the discriminability score with what they call saliency entropy to create a final significant score.
Oh. So it brings entropy back into the equation, but it alters how it's applied.
Exactly. Entropy is no longer the reward itself. It acts purely as a gatekeeper.
A gatekeeper? How so?
Stride calculates the significance of an n-gram by looking at both metrics simultaneously. First, is this phrase a critical decision point? Meaning, does it possess high generation entropy?
Okay.
And second, does this phrase actually lead to success? Meaning, does it have a high discriminability score?
So Stride only applies a reward or a penalty to a phrase if its entropy is above a certain threshold. It has to be a genuine fork in the road.
Yes. If it's a critical, high uncertainty decision point and it correlates strongly with the successful pile, it receives a targeted reward.
And if it's a critical decision point, but it correlates with the failed pile, it gets a heavy penalty.
Exactly. And those routine vocabulary words, they have low entropy because they're highly predictable, so the system simply ignores those words and focuses entirely on the high-stakes decisions.
Okay, here's where it gets really interesting. The source material provides a clear window into this mechanism working in real time. They highlight a specific math problem involving Aya's coffee shop.
Yeah, the Aya problem is a fantastic case study from their rollouts.
Walk us through it.
It's an algebra problem detailing a girl named Aya going for a walk, stopping for coffee, and changing her walking speed. Crucially, the prompt gives a specific time of 2 hours and 24 minutes.
Right. And when humans see 2 hours and 24 minutes, our cognitive instinct is often to immediately convert it into a decimal. We visualize 2.24.
Which is a trap.
A massive trap.
Yeah.
Because 24 minutes is not 24% of an hour, it's 24 out of 60, which simplifies to 2/5 or 0.4. So the correct decimal is actually 2.4.
But the AI, heavily influenced by its initial training data, which contains vast amounts of flawed human reasoning, by the way, repeatedly fell into that exact same cognitive trap.
It did the 2.24 thing.
Yeah. During its rollouts, the model generated the specific 5-gram phrase, guess decimal time from notation.
And because that specific phrase represented an active, uncertain decision like, it registered high mathematical entropy, the gatekeeper filter caught it.
Exactly. The system then looked at the discriminability score. Treating 2 hours and 24 minutes as 2.24 hours fundamentally breaks the underlying algebra.
So every time the AI generated that phrase, it ultimately failed the problem.
Yes. That specific 5-gram was overwhelmingly correlated with the failed pile.
So Stride identified that correlation and hit the phrase with a negative significance score. It weakened the probability of the AI ever generating that specific cognitive pattern again.
It systematically taught the model that guessing decimal time from notation is a trap.
That is so cool.
It gets better. Simultaneously, in the successful rollouts, the model navigated the problem differently. It bypassed the decimal trap entirely by realizing the stopping time at the coffee shop remained constant in both scenarios presented in the prompt.
Yep.
So it generated a different 5-gram phrase, derive equations from shared condition.
And that phrase also had high entropy because it was a major strategic pivot, but it highly correlated with the successful pile.
Right. Stride recognized that correlation and applied a positive significance score. It strengthened that specific cognitive habit. The system is essentially performing microsurgery on the AI's logic.
Microsurgery, I love that.
It executes this microsurgery by integrating the significance score with the overarching base reward.
So the AI still receives the broad outcome reward from the GRPO system.
Yes, but Stride reweights the individual intermediate steps within the response. It heavily boosts the derive equations in a gram, heavily penalizes the guess decimal n-gram, and completely ignores the routine grammar in between.
Which optimizes the policy model with laser precision.
Precisely.
So, since Stride is actively adjusting these microhabits and penalizing these deeply ingrained logic traps, how does that actually change the AI's performance when it's forced to take standardized, highly complex tests?
The researchers ran extensive benchmarking to prove this wasn't just an isolated anomaly. They tested Stride across multiple base models from completely different architectural families and scales.
Like which ones?
Specifically, Qwen 2.57b, Llama 3.18b, and Qwen 3.4b.
Which is smart. Testing multiple base models ensures the framework isn't just exploiting a quirk in one specific system.
Exactly. To test its mathematical reasoning, they ran the Qwen 2.57b model through a gauntlet of rigorous datasets, including Math 500, AMC, and the AIM.
And for context, the A is the American Invitational Mathematics Examination. It's brutal.
Brutal is the right word.
It's a 15-question, 3-hour exam where the answers are integers from 0 to 999. Guessing is mathematically impossible. It requires rigorous multi-step logical chaining, and it routinely trips up human mathematical prodigies.
So it's the ultimate test of logic.
How did Stride perform against the existing training methods on those exams?
They compared it against the strongest existing token-level reinforcement baseline, a method known as HE-DAPO. Across the board, Stride achieved substantial improvements.
Give us the numbers.
On average, across all the math benchmarks, it raised the base model's score from 42.18 to 44.71.
In the current landscape of large language models, where researchers fight tooth and nail for fractions of a percent, a jump of over 2 full points on elite datasets is massive.
It is highly significant. Additionally, the paper highlights how Stride scales with test time compute.
What does that mean?
This refers to giving the model more time to sample and deliberate before finalizing an answer. When they increased the number of rollouts, the model could generate scaling all the way up to 10 responses. Stride's performance pulled further and further ahead of standard GRPO.
So the longer you let it think, the more its optimized reasoning habits compound.
Exactly, particularly on those grueling tests like the AM 2024.
Okay, but math provides a very clean, structured environment for testing logic. The rules are absolute.
True.
Does this framework, this ability for the AI to audit its own multi-step reasoning, translate to environments that are messier and less structured?
Yeah.
Like, can it navigate complex visual data or interactive environments where the rules aren't just neat equations?
If we connect this to the bigger picture, that is arguably the most groundbreaking aspect of the research. Stride is not confined to being just a math-specific trick.
Okay.
The researchers extended the DSR framework to multimodal vision language models. They tested it on benchmarks that require the AI to interpret complex images, including MMU Pro, MA, and a highly specialized biology benchmark.
And it maintained its performance gains when interpreting visual data.
It saw substantial gains. On the biology benchmark specifically, applying Stride improved the base model score from an already solid 54.0 all the way to 72.3.
Wow.
Yeah, it comfortably beat out strong reinforcement learning baselines that were designed specifically and exclusively for multimodal tasks.
So it applied the exact same spot, the difference logic, to visual reasoning steps.
It did, and the researchers pushed it even further into interactive agent tasks.
What are those?
These are environments where the AI doesn't just answer a question, it has to actively navigate a simulated interface. They tested it on WebShop, which mimics an e-commerce website, and ALF World.
Oh, interesting.
In these environments, the AI has to use search bars, interpret simulated HTML, and click specific buttons. If it makes a single illogical click or goes down a useless navigation tangent, it fails the task entirely.
See, the sparse supervision problem in an interactive environment is huge.
Yeah.
If you click through 20 pages and fail, the AI has no idea which click actually doomed the mission.
Exactly. But by applying Stride, the AI learned exactly which navigational engrams led to success. In those agent tasks, Stride achieved an 84.3 average score, outperforming the strongest offline reinforcement learning baselines.
That is incredible.
The data proves that we can achieve fine-grained, step-by-step improvement in an AI's strategic thinking across text, vision, and dynamic interactive environments. And we can do it entirely automatically.
We are no longer bottlenecked by the need for expensive human annotators to sit there and subjectively grade every single reasoning step.
Precisely.
So what does this all mean? Let's synthesize the technical journey we just covered today. We started in a paradigm where AI training operated like a teacher just checking the final answer box.
That was standard GRPO.
Right, a sparse supervision framework that accidentally rewarded lucky guesses and bad logic just because the final output was correct. Then we looked at the flawed attempt to fix it, realizing that just measuring when an AI is thinking hard, looking for high mathematical entropy, is a trap, because the metrics for confusion and brilliance look identical.
They're indistinguishable.
Finally, we unpacked the solution, Stride. A framework that takes verifiable outcomes, traces them backward to locate specific multi-word decisions, filters those decisions to isolate the high-entropy critical moments, and mathematically maps out exactly which cognitive habits causally lead to success and which lead to failure.
It's an elegant solution. And, as you process the mechanics of how this system works, I want to leave you with a slightly provocative thought.
Ooh, I like provocative. Let's hear it.
Something that takes this highly technical AI framework and points it directly at the human experience.
Okay.
If an artificial intelligence can now be mathematically trained to perfectly identify its own productive reasoning habits versus its useless wheel-spinning spirals, what if we applied a Stride framework to our own human minds?
Oh, wow.
Imagine if you possessed the ability to audit your own daily decision-making patterns. Think about the mental engrams you rely on every single day.
The phrases we repeat to ourselves.
Exactly. Which of your recurring thought patterns actually causally lead you to successful outcomes? And which of your recurring thoughts are just high-entropy anxiety phrases you repeat to yourself that feel like deep, important thinking, but actually just consistently correlate with failure and inaction?
That is a deeply compelling question to mull over. We spend so much of our energy worrying about whether our final answer in life is correct, but perhaps we need to spend a little more time auditing the messy logic on our own scratchpads.
Absolutely.
Well, thank you for joining us on this deep dive into the Stride framework. Our goal is always to keep you armed with the cutting edge of what is happening in technology and research, breaking down the complex mechanisms so you don't have to wade through the dense data yourself. Stay curious, keep auditing those mental engrams, and we will catch you on the next deep dive.